Welcome, everyone, to the Deep Dive. I'm Adam.
And I'm Grace.
We're both grade 8 science teachers right here at School in X.
And we're super excited to have you, our fantastic grade 8 students, joining us for this special deep dive today.
Yeah, you know the drill by now. Our mission here is to take some of these really powerful, sometimes kind of mysterious natural phenomena.
Things that might even seem a bit scary sometimes.
Exactly. And we want to break down the science behind them, really get into the how and the why.
Right. The goal isn't just listing facts. It's about understanding the process and, really importantly, figuring out how we can stay safe.
It's about turning that maybe little bit of fear into real, informed understanding, giving you the knowledge you need.
Making you confident and safe out there in the world.
So today we're tackling two really, truly awesome natural events. First, we're looking up, way up, into the stormy sky to explore lightning.
That incredible electric flash.
And then we'll shift our focus down to the ground right under our feet to understand earthquakes, those powerful shakes.
So get ready. We're going to uncover some, well, let's say, shocking facts.
Oh, nice one. And gain some definitely groundbreaking insights. Let's jump in.
Okay, let's start with lightning. Because honestly, it's something most of you have probably experienced, even if just in a tiny way.
You see that massive bolt splitting the sky, and it just seems like this, unbelievable force, pure power.
It really does. But here's the core idea, and this is kind of an aha moment, I think. Lightning, that huge spectacle, is fundamentally just a giant version.
Wait, a giant version of what?
Of the tiny little electric sparks we run into almost every day.
Hold on. That massive, terrifying flash in a storm is basically the same physics as me, like pulling off a wool sweater in the dark. Seriously.
It sounds crazy, but yes. It all comes down to scale and how much charge builds up.
Okay, explain that scaling up. How does that little crackle become a huge thunderclap?
Well, think about it. You pull up that woolly jumper or maybe a polyester shirt, especially when it's dark and dry. What do you notice?
Yeah, you see those tiny little sparks? Maybe hear a faint crackling? Sometimes my hair even stands on end.
Exactly. That's static electricity. It's not magic, it's physics. And it's the exact same basic principle behind lightning.
Huh, okay.
Or maybe you've seen sparks on an electric pole, if the wires are a bit loose. Or even from a plug that's not quite pushed into the socket properly.
Yeah, I've seen that. Little zaps.
Those are also electrical discharges, just on a much, much smaller scale than a lightning bolt.
It's pretty wild to think how long it took us as humans to connect those dots.
Oh, totally. For thousands of years, people saw lightning and thought, divine anger, punishment from the gods.
Something terrifying because it was just completely mysterious. Imagine seeing that power and having zero explanation.
Absolutely. I mean, even the ancient Greeks, way back, like 600 BC, they knew rubbing amber with fur made it attract light things like feathers.
Right. Amber is electron in Greek. That's where we get electricity.
Exactly. But did they connect that little static cling trick to a massive lightning strike? Not at all. It seemed like two totally different things.
Until Benjamin Franklin, right?
Yeah.
Around 1752. That famous kite experiment story.
Well, yeah, the kite story is iconic, though maybe a bit embellished for safety's sake. But Franklin's insight was revolutionary. He was the one who definitively showed, or at least strongly argued, that lightning and those little static sparks were fundamentally the same phenomenon.
And that took until the mid-1700s. So like 2,000 years for humanity to figure that out.
Pretty much. It was a massive leap in understanding. It completely shifted how we saw lightning moving away from pure fear and superstition.
Towards scientific understanding, and importantly, towards figuring out how to protect ourselves from it.
Precisely. And that modern understanding is key. We now know lightning isn't some random act of fury. It's caused by a massive buildup and accumulation of electric charges inside clouds.
Knowing that helps us understand why precautions are necessary, which we'll definitely get into.
But first, let's back up a tiny bit. How do things even get charged in the first place? What creates that static electricity?
It often starts with simple rubbing, right? Friction.
Exactly. The process is called charging by rubbing, or friction. You know how rubbing your hands together makes them warm? Friction generates heat. Well, it can also generate a small electric charge.
How does that work? Is it like scraping something off?
Sort of. It's about moving incredibly tiny, invisible particles called electrons from one surface to another. When you rub two different materials together, one material might grab electrons more strongly than the other.
So one loses electrons and the other gains them.
You got it. And you can actually see this effect really easily. Grab a used plastic ball pen refill, just the inside tube, and a piece of polythene, like from a plastic bag.
Okay, got my imaginary refill in plastic.
Now rub that refill really vigorously with the polythene, like you're trying to polish it super fast.
Okay, rubbing.
Now, here's the important bit. Don't touch the end you just rubbed with your fingers or anything metal.
Oh, yeah. Because our bodies and metals can conduct the charge away, ruin the experiment.
Perfect. So carefully bring that rubbed end near some tiny pieces of paper or maybe some dry leaves, bits of husk, even tiny mustard seeds if you have them. What happens?
Ooh! The little bits jump up and stick to the refill. It's like it suddenly became magnetic, but it's not a magnet.
It's electric attraction. You can do the same thing with a plastic comb rubbed through dry hair. It'll pick up those light objects too.
So the rubbing gave the refill or the comb an electric charge.
Yes, but here's a crucial point. It's not just the object being rubbed that gets charged. The material used for rubbing the polythene or your hair also gets charged in the process.
Ah, so it's a two-way street. One gains electrons, becomes negative, the other loses them, becomes positive.
Exactly. It's always a transfer, creating opposite charges on the two objects.
Okay, so we have charged objects. How do these charges interact with each other? Is it like magnets?
It's very similar to magnets. You know how magnets can either attract or repel? Charges do the same. There's a fundamental rule.
Let me guess. Like charges repel, opposite charges attract.
You nailed it. We can demonstrate this too. Blow up 2 balloons. Rub both of them with a piece of woolen cloth.
Okay, 2 wool rub balloons.
Now, try to bring them close together, maybe hang them so they can swing freely. What do?
They should push each other away, right? Because they both got the same kind of charge from the wool.
Yeah.
They repel.
Exactly. Clear repulsion. You can see the same thing if you take 2 pen refills, rub both with polythene, suspend one, and bring the other near it. They'll push away too.
So that proves it. Charges of the same kind repel each other.
Now for the flip side, attraction. Take one of those charged balloons rubbed with wool and bring it near a charged pen refill rubbed with polythene. We know they got charged differently.
So they should pull towards each other. Attract.
And they do. They attract each other. This demonstrates the other half of the rule. Charges of different kinds attract each other. Opposites attract.
Simple rule, big consequences.
Oh.
Now, about these kinds of charges, we call them positive and negative, right?
Yes. That convention was actually set up by Benjamin Franklin. He decided, sort of arbitrarily, that the charge on a glass rod rubbed with silk would be called positive.
So silk takes electrons from the glass, making the glass positive.
That's the modern interpretation, yes. And then, if you rub, say, a plastic straw with polythene, that straw gains a negative charge. How do we know? Because it's attracted to that positively charged glass rod.
Okay, so positive and negative are just labels, but they help us track the interactions. And you mentioned static electricity earlier.
Yeah.
These charges we're creating by rubbing, they just sit there, right? They're static.
Good point. Yes, these are static charges. They accumulate on the surface of the object and generally don't move unless they have a path to go somewhere. This is different from
Electric current, like in wires. That's when charges are actually moving, flowing along.
Exactly. Static is stationary charge. Current is moving charge. Two related but different concepts.
Got it.
Yeah.
So we can create these charges. We know how they interact. How do we actually detect if something has a charge, maybe a bigger one? And how do these charges eventually, disappear or neutralize?
Great questions. That brings us to a really neat, simple device called an electroscope and a super important safety concept called earthing or grounding.
An electroscope. Sounds fancy. Is it hard to make?
Not at all. You can actually make a basic one pretty easily. You need an empty jam jar, a piece of cardboard for a lid, make it a bit bigger than the jar opening.
Okay, jam jar, cardboard lid.
Punch a small hole right in the middle of the cardboard. Then take a metal paper clip, straighten it out mostly, but leave or make a little hook at one end.
Paper clip straightened, hook at the bottom. Got it.
Poke the straight end of the paper clip up through the hole in the cardboard lid, so the hook hangs down inside where the jar will be. Now get some aluminum foil, like kitchen foil. Cut 2 small, thin strips, maybe 4 centimeters long, 1 centimeter wide, really light.
Thin foil strips.
Carefully hang both foil strips on the hook of the paper clip inside the jar area. Then put the cardboard lid on the jam jar with the paper clip sticking up and the foil strips hanging down inside, not touching the bottom or sides ideally.
Voila, a homemade electroscope. So, how does this little gadget work?
It's clever. Take that charged object again, maybe your rubbed pen refill. Gently touch the top end of the paper clip, the part sticking out of the lid, with the charged refill.
Okay, touching the clip.
What happens is the charge from the refill transfers through the metal paperclip. Metal's a good conductor, remember. It lets charge move easily.
Right, the charge flows down the clip.
To those two little aluminum foil strips hanging on the hook. Now think. Both strips get the same kind of charge from the refill. And what do, charges do?
They repel, push each other apart.
Exactly. So the two lightweight foil strips will push away from each other. They'll spread wide open like little wings.
So the more charge you transfer, the wider they spread.
Precisely. This simple device lets you detect if an object is charged and roughly how much charge it has just by seeing how much those foil leaves diverge or spread apart.
That's pretty neat. Okay, now how do we make them go back down? How does the charge disappear?
This leads directly to earthing. Try this. While the foil strips are spread apart because the electroscope is charged, gently touch the top of the paperclip with your finger. Just briefly touch it.
Touching the clip of my finger. What happens to the foil strips?
They instantly collapse. They fall right back down to their original position, hanging straight.
Whoa. Why? Did my finger suck up the charge?
In a way, yes. Your body is a reasonably good conductor, mostly because we're full of water and dissolved salts. And the Earth itself is like a giant reservoir for electric charge. It can absorb or give up a huge amount of charge without really changing its own overall charge significantly.
So when I touched the clip, the charge on the foil strips traveled through the clip, through my body.
And into the Earth. You provided a pathway for the charge to escape to the ground.
That's called earthing.
Exactly. Earthing or grounding, you'll hear both terms, is just the process of transferring charge from a charged object directly to the Earth.
And this isn't just for science experiments, is it? You mentioned safety.
Absolutely vital for safety. Earthing is built into our homes and buildings. Those third round prongs on some electrical plugs, that connects to the earthing wire in your house wiring.
What does that do?
It protects you from electric shocks. If there's a fault, say, a live wire inside an appliance accidentally touches the metal casing.
Like on a toaster or a washing machine.
Right. Without earthing, that whole metal casing could become live, dangerous to touch. But the earth wire provides a safe, low-resistance path for that dangerous current to flow directly into the ground, usually tripping a circuit breaker or blowing a fuse in the process.
So the electricity takes the easy path to the ground instead of going through me if I touch the faulty appliance.
Precisely. It's a life-saving safety feature. It gives stray electricity a safe exit route.
Okay, that makes total sense. So we've got sparks, charge buildup, attraction repulsion, detecting charge, and earthing.
Mm-hmm.
How does this all come together to create lightning?
Now we can paint the full picture. Remember, lightning is electric discharge, just on an absolutely massive scale. It all starts inside those big, turbulent thunderstorm clouds.
What's going on in there? It looks chaotic from the ground.
It is. You have incredibly strong air currents, updrafts, carrying tiny water droplets and ice crystals way up high. At the same time, heavier water droplets, hail, maybe slushy ice particles called graupel, are falling downwards.
So it's like a giant high-speed collision zone up there.
Exactly. All these particles, water, ice, hail, are constantly bumping into each other, rubbing against each other, colliding violently, and just like rubbing the pen refill with polythene.
These collisions transfer charge. Electrons get knocked off some particles and grabbed by others.
Right. It's like countless tiny friction experiments happening constantly throughout the cloud. This leads to a massive separation of electric charge within the cloud.
Okay, so charge gets separated. Does it collect in specific places?
Generally, yes. While the exact mechanisms are still researched, the typical pattern is that the lighter positively charged particles, like small ice crystals, get carried upwards by the strong updrafts. So positive charge tends to accumulate near the top of the cloud.
And the negative charge.
The heavier, negatively charged particles, like graupel or larger ice particles, tend to sink or accumulate near the lower parts of the cloud. So you get this distinct layering. Positive up high, negative down low.
What about the ground below the storm?
Good question. The large negative charge accumulating at the base of the cloud actually repels negative charges in the ground beneath it, pushing them away. This leaves the surface of the ground directly under the storm with an induced positive charge.
Okay, so we have this huge separation, positive cloud top, negative cloud base, and positive ground. That sounds like a recipe for, well, something big to happen.
It is. You've got these enormous regions of opposite charge building up, separated by the air. Now, air is normally a pretty good insulator, right? It doesn't conduct electricity easily.
Yeah, otherwise we'd be getting zapped all the time.
Exactly. The air acts like a barrier, trying to keep those massive positive and negative charges apart. It resists the flow of charge.
But it can't hold out forever.
Not when the charge difference, the electrical potential, becomes incredibly large. When the sheer amount of accumulated positive and negative charge gets too massive, the insulating capacity of the air simply breaks down. It can't resist anymore.
And that's when lightning happens.
That's the critical moment. The air suddenly becomes conductive along a path, and the negative charges rush down from the cloud base to meet the positive charges rising up from the ground. Or sometimes positive charges stream down from the top. This rapid, massive flow of charge heats the air path to incredibly high temperatures, hotter than the surface of the sun.
Wow. And that superheated air is what creates the bright flash.
Exactly. That brilliant, blinding streak of light is the lightning, caused by the incandescence of the superheated air channel. And that same sudden, explosive expansion of the rapidly heated air creates a shock wave.
Which we hear as thunder.
Precisely. Light travels much faster than sound, so you see the lightning flash almost instantly, but the thunder takes time to reach you. The whole process, this sudden equalization of charge through the air, is called electric discharge.
And does it always go from cloud to ground? I've seen flashes just light up the clouds.
Good observation. No, it doesn't always go to the ground. Electric discharge can happen between different charge regions within the same cloud, that's intracloud lightning, the most common type, or between two separate clouds, cloud-to-cloud lightning, or, of course, between the cloud and the Earth, cloud-to-ground lightning.
So even though we understand the science now, it's still incredibly powerful and dangerous.
Absolutely. Knowing the science helps us respect its power and take the right precautions. It's not divine wrath, but it's definitely not something to mess with.
Which brings us neatly to lightning safety. This is super important, grade 8, so listen up.
The number one rule: if you can hear thunder, you are close enough to be struck by lightning. Thunder is nature's warning signal.
So hear thunder.
Immediately seek safe shelter. Don't wait for the rain or for the lightning to look closer. Head indoors right away. And wait a good while after the last thunderclap before going back out. The usual advice is about 30 minutes.
Okay, so what counts as a safe shelter?
The best options are substantial buildings, your house, school, a library, a shop. Buildings with proper wiring and plumbing offer excellent protection.
What about if you're in a car?
A hardtop car or bus with all the windows and doors closed is also a very safe place. It's because of that metal shell we mentioned earlier.
The Faraday cage effect. The electricity goes around the outside.
Exactly. The metal conducts the charge safely around the occupants and into the ground.
So those are the safe places. What about the unsafe places? Where should you definitely not be?
Okay, outdoors is generally much riskier. Avoid open vehicles completely. Things like motorbikes, tractors, golf carts, convertibles with the top down, no protection there.
Open fields are bad too, right? Especially if you're the tallest thing around.
Very dangerous. Also avoid tall, isolated trees. Lightning often strikes the tallest object in an area. Being under a tall tree is one of the riskiest places to be.
What about park shelters? Like those picnic pavilions?
If they're not fully enclosed buildings, they offer little protection. Also avoid elevated places like hilltops or ridges, and definitely do not carry an umbrella.
Why the umbrella? Seems like it would keep you dry.
It might keep you dry, but that metal pole sticking up can act like a mini lightning rod, potentially attracting a strike right to you. Not worth the risk.
Okay, so what if you are caught outdoors and there's no proper building or car nearby, like you're hiking in a forest or out in a field?
Right, emergency situation. If you're in a forest, don't shelter under the tallest trees. Look for a dense stand of shorter trees and stay low.
And if you're in a completely open field, no trees, no nothing.
Get as far away as possible from any isolated trees, poles, metal fences, anything conductive. Then, and this is crucial, do not lie flat on the ground.
Why not lie flat? Seems like making yourself small.
Lying flat increases your contact area with the ground. If lightning strikes nearby, dangerous currents can travel through the ground, and a larger contact area means more current could potentially flow through you. It's called ground current.
So what do you do?
You should squat low to the ground, on the balls of your feet if possible, to minimize contact. Put your hands on your knees and take your head down between your hands. Make yourself the smallest possible target vertically while minimizing ground contact. It's not perfect, but it's the recommended safety posture.
Okay, squat low, head down, minimal contact.
Oh.
Got it. Now, what about safety inside the house? Are we totally safe once we're indoors?
Mostly, but there's still a few precautions. Remember, lightning is electricity, and it can travel through wiring and plumbing. So avoid contact with anything connected to those systems. Don't use corded phones. Landlines. Mobile phones and cordless phones are generally safe as they aren't physically connected to the outside lines. Although, avoid using a cordless phone base unit that's plugged in.
Okay, no corded phones. What else?
Avoid contact with electrical wires and metal pipes. This means don't take a shower or bath during a thunderstorm. Don't wash dishes or do laundry. Water pipes can conduct electricity if lightning strikes the building or nearby.
Right, water safety is key. What about electronics?
It's a good idea to unplug sensitive electronic appliances like computers, TVs, gaming consoles. Lightning can cause power surges that travel through electrical wiring and damage them, even if the strike isn't direct.
Do we need to turn off the lights?
No, electrical lights are generally fine to leave on. They're less sensitive than complex electronics.
Okay, so avoid water, corded phones, electronics. Sounds doable. You mentioned lightning conductors earlier for buildings.
Yeah.
How exactly do they work?
Right, lightning conductors or lightning rods. They're specifically designed to protect buildings. It's typically a metal rod, often copper or aluminum, installed so it's the highest point on the building.
Taller than the chimney or antennas?
Yes, taller than everything else. One end is pointed up in the air. The other end is connected via a thick metal cable down the side of the building, and then it's buried deep in the ground, often connected to a metal plate or grid.
So what does it do if lightning heads for the building?
It provides a safe, easy, low-resistance path for the lightning current to follow. Instead of the lightning blasting through the roof or walls, which could cause fires or structural damage, it strikes the rod
Travels down the cable.
and is harmlessly discharged deep into the earth. It basically intercepts the strike and guides it safely away from the building itself. It gives the lightning a preferred route to ground.
Like a dedicated highway for the electricity.
Exactly. And while other metal things in a building, like metal structural columns, wiring conduits, water pipes, can offer some unintentional paths to ground.
We still shouldn't touch them during a storm.
Definitely not. Rely on the dedicated lightning protection system if one is installed, and follow the indoor safety rules regardless.
Okay, that's a really thorough look at lightning. From tiny sparks to safety measures. So powerful, but understandable with science.
It really is. Now, should we shift our focus from the sky down to the earth itself?
Let's do it. Earthquakes. The ground we stand on usually feels so solid, so reliable. But sometimes it shakes violently.
It's a stark reminder that our planet is incredibly dynamic. An earthquake is basically a sudden shaking or trembling of the Earth's surface. It usually lasts for only a very short time, maybe seconds or minutes, but the effects can be immense.
And it's caused by something happening deep inside the Earth, not on the surface.
That's right. It's caused by a sudden release of energy, a disturbance, deep within the Earth's crust, its outermost layer.
Is it happening all the time? Or are they rare?
This surprises a lot of people. Earthquakes are happening constantly all over the world, every single day, thousands of them.
Thousands? Why don't we feel them all?
Because most of them are incredibly small microquakes. Too faint to be felt by humans, only detectable by sensitive instruments. They're just tiny adjustments in the crust.
But then there are the major ones, the big ones.
Exactly. Major earthquakes are much less frequent, thankfully, but when they do happen, they can cause catastrophic damage. Buildings, bridges, dams can be destroyed.
And tragically, they often lead to significant loss of life and property damage. The shaking itself is devastating.
And it's not just the shaking. Major earthquakes can trigger other disasters too, like secondary hazards.
What kind of things?
They can cause devastating landslides, especially in mountainous areas. They can break dams or levees, leading to floods. And if a powerful earthquake happens under the ocean,
Tsunamis, those huge ocean waves.
precisely, a large undersea earthquake can suddenly displace a massive amount of water, creating a series of powerful waves that can travel across entire oceans and inundate coastal areas. We saw the horrific impact of this with the Indian Ocean tsunami back on December 26, 2004. It showed how one disaster can cascade into another.
And the really scary thing about earthquakes, compared to storms, is that we can't predict them right.
That is the crucial and frankly sobering difference. Despite decades of research and incredibly sensitive monitoring, scientists cannot yet accurately predict exactly when or where the next major earthquake will strike. We know the regions that are prone to them, the fault zones, but the precise timing? No.
Which makes being prepared even more critical,
Mm-hmm.
especially in those known high-risk areas.
Absolutely. We've seen the terrible consequences in India, unfortunately. Major earthquakes like the one in Uri and Tandar in North Kashmir on October 8, 2005, or the Bhuj earthquake in Gujarat on January 26, 2001, Both caused widespread destruction and loss of life, reminding us how vital preparedness is.
So let's get into the cause. Why does the Earth shake like that? What's happening down there?
It mostly comes down to something called plate tectonics. Think of the Earth's outer layer, the crust and the upper part of the mantle, as not being one solid piece. It's broken up.
Like a cracked eggshell.
Kind of. It's fragmented into huge, irregularly shaped slabs or pieces called tectonic plates. Some plates carry continents, others carry oceans, some carry both, and they're enormous.
And these plates, they move.
They do. They're constantly slowly moving, floating on the hotter, more fluid layer beneath them called the asthenosphere. They only move maybe a few centimeters per year, about the speed your fingernails grow.
Doesn't sound very fast.
It's not fast on a human timescale, but these are continent-sized pieces of rock. Even moving slowly when they interact, the forces involved are absolutely immense.
How do they interact?
They can grind past each other horizontally. They can collide head-on, pushing each other up to form mountains. Or they can pull apart, allowing molten rock to rise and form new crust. It's this constant pushing, pulling, and grinding
That builds up stress in the rocks.
Exactly. Stress builds up along the boundaries where these plates meet. These boundaries are called faults, or fault zones. They're essentially giant cracks in the Earth's crust.
So the earthquake happens when the stress gets too much.
Precisely. The rocks along the fault are locked together by friction, but the plates keep trying to move. Eventually, the built-up stress overcomes the friction, and the rocks suddenly slip or rupture, releasing all that stored energy in the form of seismic waves.
And those waves travel outwards, shaking the ground.
That's the earthquake. These plate boundaries, these fault zones, are the weak spots in the crust where most earthquakes occur. That's why some regions are much more earthquake-prone than others. They're sitting on or near these active boundaries.
Are there specific types of boundaries linked to specific quake types?
Generally, yes. Where plates pull apart, divergent boundaries, like mid-ocean ridges, you tend to get shallower, less powerful quakes. Where they slide past each other, transform boundaries, like the San Andreas Fault, you can get frequent, sometimes strong, shallow quakes. And where they collide, convergent boundaries, especially where one plate dives under another, you can get the deepest and most powerful earthquakes, often associated with mountain ranges or volcanic arcs.
What about India? Which areas are most at risk?
India has several high-risk zones because the Indian plate is actively colliding with the Eurasian plate. That's what formed the Himalayas. So the most threatened areas include Kashmir, the entire western central Himalayas, all of the northeast region, the Rann of Kutch in Gujarat, parts of Rajasthan, and the Indo-Gangetic Plain, which sits just south of the Himalayas.
So quite large areas.
Yes, and even some parts of South India fall into what's considered a moderate danger zone, though the risk level is generally lower than in the Himalayan belt.
Are tectonic plates the only cause of earthquakes?
They cause the vast majority, probably over 90% of all earthquakes, and certainly almost all the major ones. But other things can cause tremors.
Like what?
Major volcanic eruptions can shake the ground significantly as magma moves. Very large meteorite impacts would cause huge shockwaves. And on a human scale, large underground explosions, like nuclear tests, also generate seismic waves that look very much like small earthquakes on seismographs.
But mostly, it's those giant plates shifting around. It really shows how alive the planet is, geologically speaking.
Absolutely. It's a constantly reshaping dynamic system.
So if an earthquake happens, how do scientists actually measure it? How do they know how big it was or where it started?
They use those seismic waves we mentioned. When a fault ruptures, it sends out different types of waves that travel through the Earth. Some travel along the surface, causing most of the shaking we feel, while others travel deeper through the Earth's interior.
And we record these waves.
Yes, using an instrument called a seismograph. Modern seismographs are incredibly sensitive, but the basic principle is quite simple.
How does it work?
Essentially, you have a heavy weight, a mass, that's suspended so it can swing or vibrate freely, often like a pendulum. This weight is attached to a frame that's firmly anchored to the ground.
Okay, heavy weight suspended.
When the ground starts shaking during an earthquake, the frame and the recording drum or sensor move with the ground. But the heavy weight, due to its inertia, tends to stay relatively still or lag behind the ground motion.
So the pen or sensor attached to the weight records the difference in movement between the steady weight and the shaking ground.
Exactly. A pen attached to the weight draws a wiggly line on a rotating drum of paper in older models, or a sensor converts the motion into electronic signals in modern ones. That wiggly line is called a seismogram, the recording of the seismic waves.
And scientists can read that seismogram.
Yes. By analyzing the seismograms recorded by multiple seismographs in different locations, scientists can figure out a lot. They can determine the time the earthquake occurred, locate its epicenter, the point on the surface directly above the quake's origin, estimate its depth, and understand the type of faulting that happened.
And they can figure out how powerful it was.
Yes, that's where the magnitude scales come in, like the famous Richter scale.
How does the Richter scale work? I hear numbers like magnitude 6, magnitude 7.
The Richter scale measures the magnitude, which relates to the amount of energy released by the earthquake. It's based on the amplitude, the height of the wiggles recorded on the seismogram, adjusted for the distance from the earthquake.
Is it a simple 1, 2, 3 scale? Like is a 6 twice as strong as a 3?
No, and this is really important. It's a logarithmic scale. Each whole number increase on the Richter scale represents a 10-fold increase in the measured amplitude of the seismic waves.
10 times bigger jump for each number.
10 times bigger in terms of the ground shaking recorded on the seismograph, and in terms of the actual energy released. Each whole number step up represents about 32 times more energy released.
Wow, so a magnitude 7 isn't just a bit worse than a 6.
It's about 10 times more shaking and releases over 30 times more energy. That's why the damage increases so dramatically with higher magnitudes.
What magnitude starts causing serious damage?
Generally, earthquakes with magnitudes higher than 6 can cause significant damage, especially in populated areas with vulnerable buildings. Those above 7 are considered major earthquakes, capable of widespread, heavy damage. And remember those Bhuj and Kashmir earthquakes.
Yeah, you said they were devastating.
Both had magnitudes greater than 7.5. Earthquakes of magnitude 8 or 9 are truly catastrophic, but thankfully much rarer. The scale really helps us grasp the immense power difference.
Okay, so huge power. Impossible to predict. That means preparedness is everything.
Absolutely. Since we can't know when the next big one will hit, taking precautions all the time is crucial, especially if you live in one of those known seismic zones.
What's the most important precaution? Stronger buildings.
That's definitely a major one. Designing and building structures that can withstand strong shaking is key. And modern engineering has made huge strides in this. It's called earthquake-resistant design.
How does that work? Do they just make buildings super rigid?
Not necessarily rigid. Sometimes flexibility is better. The goal is to help the building absorb the earthquake's energy without collapsing. This can involve using flexible materials, reinforcing joints, and sometimes using sophisticated techniques like base isolation.
Base isolation, what's that?
It involves putting pads or bearings, often made of rubber and steel, between the building's foundation and the ground. These pads can flex and move during an earthquake, absorbing much of the shaking energy so less of it travels up into the building itself. It's like putting shock absorbers under the whole structure.
That sounds smart. Are simply buildings safer?
Often, yes. Simpler, more symmetrical structures tend to perform better than complex, irregular ones. And it's absolutely vital to consult qualified architects and structural engineers when building in seismic zones. They know the specific codes and techniques needed.
What about building materials? Does that matter?
It does. In highly seismic areas, sometimes lighter materials like timber or even reinforced mud adobe might be preferable to very heavy materials like unreinforced brick or concrete blocks.
Why lighter?
Because if the structure does fail, lighter materials are less likely to cause severe injury when they fall. Keeping roofs as light as possible is also a key principle for the same reason: reduce the weight overhead.
Makes sense. What about inside our homes? Things we can do right now?
Yes, definitely. Secure heavy furniture like cupboards, bookcases, and shelves firmly to the walls using brackets or straps. This stops them from toppling over during shaking.
That seems like an easy fix that could prevent injury.
It really can. Also, think carefully about where you hang heavy items like wall clocks, large picture frames, or mirrors. Don't hang them over beds or sofas where people sit or sleep. Make sure water heaters are securely strapped down too.
Good tips.
Yep.
Anything else indoors?
Since earthquakes can break gas lines or damage electrical wiring, fires are a real secondary hazard. So it's essential that buildings, especially taller ones, have working firefighting equipment, extinguishers, maybe sprinkler systems, and that people know how to use them safely. Having an emergency kit and a family plan is also crucial.
Okay, that covers preparedness. Now, the critical moment. The earthquake is actually happening. What do you do if you're at home?
If you are indoors, the best advice is usually drop, cover, and hold on.
Drop, cover, hold on. Break that down.
Drop down onto your hands and knees immediately. This prevents you from being knocked over but allows you to move if necessary. Cover your head and neck with your arms. If there's a sturdy table or desk nearby, crawl underneath it for shelter. Hold on to the table leg firmly until the shaking stops.
Why under the table?
It provides protection from falling debris. If there's no table, crawl next to an interior wall away from windows and cover your head and neck. Stay away from windows, glass, outside doors and walls, and anything heavy that could fall, like light fixtures or furniture.
What if you're in bed?
Stay there. Don't try to get up during the shaking. Just cover your head and neck with a pillow.
Okay, drop, cover, hold on if indoors. What if you're outdoors when it hits?
Move away from buildings. Find a clear, open spot, far from buildings, trees, streetlights, and especially overhead power lines. All of these can fall. Once you're in the open, drop to the ground and cover your head. Stay there until the shaking stops. Avoid bridges or underpasses.
And if you're in a car or a bus?
Stay inside. Pull over to a clear location as quickly and safely as possible. Stop the car, but stay inside. Avoid stopping near or under buildings, trees, overpasses, or utility wires. Once the shaking stops, proceed cautiously, watching out for road damage, cracks, or debris. The vehicle offers some protection.
Okay, great advice for staying safe during the shaking itself.
So let's wrap things up. We've covered a lot of ground today, both literally and figuratively.
We really have. We started with lightning, seeing how that tiny static spark you get from a sweater is the same basic physics as a giant lightning bolt, just scaled way, way up.
We talked about how charge builds up through friction and interaction inside clouds, leading to that massive electric discharge. And crucially, all those safety tips, seeking shelter, avoiding conductors indoors and out, the squat position, lightning rods.
Then we dove deep into the earth, understanding how those immense tectonic plates are constantly moving, building up stress along fault lines.
Leading to earthquakes. We learned how seismographs record the seismic waves, how the logarithmic Richter scale measures their immense power, and again, the importance of preparedness since we can't predict them.
Things like earthquake-resistant building design, securing furniture, and knowing exactly what to do. Drop, cover, and hold on.
And remember, grade 8, understanding all this science isn't just about passing tests, though hopefully it helps with that too.
Right. It's about gaining real insight. Knowledge that empowers you to look at these powerful natural events, not just with awe, but with understanding.
It helps you make informed decisions, enhances your safety, and lets you appreciate the incredible forces shaping our planet, shifting away from old fears towards modern, science-based preparedness.
It really is amazing when you think about it. How does understanding these hidden forces, chart separation, miles up, tectonic plates grinding deep below, change how you see the world around you?
Yeah.
The sky above, the ground beneath. Does it feel different now?
And it makes you wonder, doesn't it? What other natural mysteries are we still working to understand? What's the next big scientific puzzle about our planet or the universe that we're trying to solve?
That constant exploration, that process of discovery, asking questions, finding answers, that's what makes science so incredibly exciting.
So keep that curiosity alive. Keep observing. Keep asking why. Keep diving deep into your grade 8 science studies and beyond.
There's always more to learn, more to understand about our amazing world. Thanks for joining us on The Deep Dive.